In the deep quiet after a massive star has died, something small is left behind. It is not small in the way a stone is small, or a moon is small, or a dark planet drifting between suns is small. It is small only in size, in weight, in gravity, and in the way it bends the space around it. It belongs to a stranger part of the universe. A neutron star can be no wider than a city, and yet it can hold more mass than the sun. It is the crushed heart of a dead giant, pressed so tightly that ordinary atoms no longer survive in any familiar form. Electrons and protons have been forced together. Matter has been changed into something colder, denser, and far less forgiving than anything found on Earth. Around such an object, space does not sit still. Light leaving its surface must climb through gravity so deep that its color can be stretched. Time itself runs differently there. Not because time is broken, but because gravity has changed the shape of the path through which time moves. Far from the star, a clock would keep one rhythm. Near the star, another rhythm would unfold. The strange part is that both clocks would be right. This is where neutron stars become more than the remains of dead suns. They become places where physics is compressed into its sharpest form. They spin in darkness. Some flash like distant lighthouses. Some carry magnetic fields so strong that matter itself begins to lose its ordinary meaning. Deep inside them, beneath a surface no human machine could touch, may be forms of matter that have never existed in any laboratory. And still, they remain out there, silent and exact, turning slowly or impossibly fast in the dark, holding in their small bodies the weight of collapsed stars and the unfinished story of time. Long before a neutron star exists, there is a massive star holding itself open against its own weight. From far away, it may look simple, only a bright point fixed in the dark, steady enough to seem permanent. But deep inside it, beneath oceans of plasma and light, two forces are pressing against one another with a patience that can last for millions of years. Gravity pulls inward. It pulls on every layer, every particle, every hot stream of gas that belongs to the star. At the center, nuclear fusion pushes back. In the core, light elements are forced together so tightly that they become heavier elements, and in that change, energy is released. The energy moves outward as heat, radiation, and pressure. It is not gentle, but it is balanced. For most of the star's life, this is enough. A star lives inside that balance. It does not burn the way a candle burns. It does not feed on air. It is a deep engine of matter, changing one kind of atom into another, under temperatures and pressures that have almost no meaning in ordinary life. Hydrogen becomes helium. Later, in stars massive enough, helium becomes carbon and oxygen. The core grows heavier as the star ages, and each new fuel gives it a shorter chapter than the one before. The outside does not show the end at once. The surface may still glow. Light may still cross space from the star to distant worlds, arriving as a calm point in a night sky. If some cold planet circles far away, its frozen ground may still receive that light, as if nothing has changed. But inside the star, the center is becoming crowded with the ash of its own burning. The long balance is narrowing. There is no decision in this. The star does not choose to die. It only follows the rules that shaped it from the beginning. The more massive the star is, the faster it spends its fuel. A smaller star can last for ages, living slowly, saving itself. A massive star shines harder. It gives away its energy quickly. Its brightness is also its debt. Near the end, the core begins to build heavier elements in shells. Different layers burn in different ways, like nested regions of heat wrapped around the center. Hydrogen may burn in an outer shell. Helium may burn deeper in. Carbon, neon, oxygen, and silicon may take their places closer to the middle. The structure becomes layered, but not peaceful. It is an old star trying to keep the center from falling. Then iron appears. Iron changes the story. For a massive star, iron is not a useful fuel in the same way that lighter elements were. When lighter nuclei fuse, they can release energy and help hold the star up. Iron sits near the end of that path, Trying to draw more energy from iron does not support the star. It removes support instead. The core has reached a kind of quiet wall. The outward pressure weakens. Gravity has not become stronger. It has simply waited long enough. When the support fails, the center begins to fall inward. The collapse starts where the weight is greatest, in the innermost core. It happens so quickly that the outer layers cannot respond at first. The heart of the star drops beneath them. Matter that once took millions of years to arrange neutrons is forced into a new state in less than the span of a breath. These neutrinos are almost ghost-like familiar form, able to pass through ordinary matter which normally live around atomic nuclei. During the collapse, are driven into protons are made under that they carry away an enormous part of the dying core's energy. The core keeps falling. Density rises until matter begins to resemble the interior of an atomic nucleus. Not in chemistry, but in compression. The particles are crowded so closely that ordinary descriptions stop being useful. There is no room left for atoms, as they are known on Earth. The matter is being rewritten by pressure. Then the collapse meets resistance. The resistance is not a floor. It is not a hard surface waiting inside the star. It comes from quantum physics, from the rules that determine how particles can occupy space. Neutrons cannot simply be pushed together without limit in the same easy way that dust can be packed into a jar. At these densities, the behavior of matter becomes a force that can oppose gravity, at least for a time. The inner core stiffens. Falling material strikes it. A shock wave begins to move outward. The star, which once held itself together by a slow balance of inward weight and outward pressure, now releases that balance violently. The outer layers are driven away from the core. A supernova begins. Though from the center of the event, the word explosion is almost too simple. It is collapse and rebound, neutrinos and shock waves, falling matter and escaping light, all occurring inside the broken body of a star. From far across space, the dying star may brighten until it outshines many of the stars around it. What was once a single point becomes a signal. It announces that a massive star has ended. For a while, the supernova can pour light into space with a brilliance that seems new, even though it is the visible sign of an ending. The outer layers expand. They carry with them elements that were forged in the star's long life and in its final moments. Oxygen, silicon, iron, and other heavy nuclei move outward into the surrounding dark. Over long ages, this material may mix with interstellar gas. It may become part of new stars. It may become dust, rock, metal, or the hidden minerals of planets not yet formed. The universe wastes very little. At the center of this widening cloud, something remains. It is not the old star. It is not the bright surface that once filled space with light. It is the crushed core, compact and hot, made mostly of neutrons, held together by gravity and by the strange pressure of matter, forced into one of its most crowded forms. This remnant is the neutron star. It may contain more mass than the sun, yet its width may be comparable to that of a city. The mind expects weight to arrive with size. Mountains are large, planets are larger, stars are larger still. A neutron star breaks that habit. It keeps the mass of a star inside a sphere so small that ordinary geography could almost measure it. A line across it could fit within a region on Earth. Its gravity, however, belongs to something far heavier than any city. The surface is not a surface in the familiar sense. It is not ground waiting under an atmosphere. It is a crust of compressed matter, lying above deeper layers that become stranger with depth. Gravity there is so strong that anything loose would be pulled flat. A small fall near the surface would release more energy than a fall from any height familiar to Earth. The direction called down becomes absolute. Light itself must work to leave. The newborn neutron star is intensely hot. Its surface can shine in X-rays, and its interior holds heat left from the collapse. But it is not hot like a fire in air. It is hot like matter that has been crushed out of its old form. Cooling is slow. Energy escapes through radiation and neutrinos, through processes that depend on the hidden structure of the star. The remnant may cool for thousands, then millions of years. while still carrying the memory of the moment it formed. It also spins. The original star had rotation before it died. Most stars rotate, even if the motion seems slow across their enormous size. When the core collapses, that rotation is carried inward. A wide object becomes a small one. The spin speeds up. The same principle can be seen in a skater drawing in the arms, but near a neutron star the comparison becomes almost too small for the scale involved. A core that once turned slowly can become a remnant, rotating many times each second. The magnetic field is carried inward as well. Fields that once threaded a large stellar core are compressed into a much smaller space. The result can be a magnetic field far beyond anything made in human laboratories. In some neutron stars, this field shapes the radiation that escapes. In others, it becomes so strong that it changes how matter behaves around the star. But at the beginning, before the later names and categories, before pulsars and magnetars, there is only the remnant itself. A dead star has left behind a compact object where mass, heat, rotation, and magnetic force have all been squeezed into a narrow sphere. Around it, the supernova debris expands in a slowly thinning shell. The old star is moving outward as gas and dust. The new object remains near the center, small and heavy. Sometimes the explosion is not perfectly even. The newborn neutron star can receive a kick, a push from the asymmetry of its own birth. It may travel through space at great speed, leaving the center of the old remnant behind. A star that once lived in one place can die and send its core wandering. The surrounding gas continues to expand. The neutron star moves on, dim invisible light, but still present in X-rays, radio signals, or the sweep of its rotating beam. There is a quiet change in scale here. The massive star belonged to the visible universe of bright points and glowing clouds. The neutron star belongs to the hidden universe of density, gravity, and time. It is not impressive because it is large. It is difficult to understand because it is small and still contains so much. Its size invites comparison with cities. Its mass refuses all ordinary comparison. The old star lived by fusion. The neutron star persists by compression. Fusion made pressure and light. Compression makes density and curvature. Around the remnant, space is no longer shaped in a mild way. It bends more sharply. Light leaving the surface is stretched. Time near the star does not pass in quite the same way as time far away. These effects are not decorations added to the object. They come from what it is. To reach that point, the story must begin with the dying star. Not with time, not with the clock, not yet with the strange bending of light, but with the final failure of a balance that once kept a giant star open. The star spends its life holding gravity back. When it can no longer do so, the center falls, matter changes. The outer layers are thrown into space, the core remains. A neutron star is born from that remaining core, and its birth is less like a new flame than a closing fist. The universe takes something wide and shining and folds it inward until almost nothing familiar is left. What remains is not empty, not dead in any simple sense, and not quiet in its physics. It is a dense turning object, still cooling, still bending space, still carrying the history of the star that made it. The supernova fades. The glowing gas spreads thinner. The surrounding stars keep their distance, each one moving through its own long life. At the center, or perhaps already racing away from it, the neutron star continues. Gravity pulls inward. Matter resists. The question is held in that balance. For now, the answer is still no. The remnant left behind after the supernova is sometimes described as city-sized. But that phrase can be misleading if it makes the object feel familiar. A city has streets, air, distance, empty rooms, and space between walls. A neutron star has almost none of that kind of emptiness. It is closer to the idea of a sun that has been pressed inward until the ordinary architecture of matter has vanished. Its width may be only about the distance from one side of a large city to the other. Across Earth, Such a distance can be crossed in an afternoon. A river may run through it. Buildings may rise along it. Clouds may pass over it. That same span, placed across a neutron star, would contain more mass than the Sun. The comparison is almost too quiet for what it means. The star is small. The weight is not. The surface gravity is so strong that the shape of the star becomes very close to a perfect sphere. Mountains, if they exist at all, cannot rise like mountains on Earth. They would be pressed down by gravity until even the tallest irregularities are tiny by ordinary standards. A feature that would count as a small wrinkle on Earth may represent a great strain on the crust of a neutron star. The landscape has been flattened by weight. Yet the surface is not smooth in the gentle way of water. It is a crust of compressed material, likely made of nuclei and electrons, arranged under pressure that rises with depth. Near the outside, matter may still have some connection to familiar atomic structure, though distorted by gravity and density. Deeper down, nuclei become more neutron-rich, packed closer together as electrons are forced into protons. The deeper the journey goes, the less matter resembles anything from ordinary chemistry. In the outer crust, atomic nuclei may sit in a lattice, not unlike a crystal, but under conditions far beyond any mineral on Earth. The pressure is so high that atoms cannot keep the spacious arrangement they have in rocks, metals, or living tissue. Electrons move through the material in a dense sea. The nuclei grow heavier and stranger as depth increases, holding more neutrons than stable atoms can hold under normal conditions. Below that, in the inner crust, the matter changes again. Neutrons begin to drip out of nuclei. This phrase sounds almost soft, but the process is not liquid dripping from a leaf. It means that the nuclei can no longer hold all their neutrons inside. Some neutrons become free to move through the crust, forming a strange mixture of neutron-rich nuclei, electrons, and free neutrons under immense pressure. The star becomes less like a solid object and more like layered nuclear matter. There may be structures there that physicists call nuclear pasta. The name is almost too ordinary for such a place. It refers to shapes that dense nuclear matter may form under competing forces. Some regions may arrange themselves into sheets, rods, or other patterns, because the nuclear force pulls matter together, while electric forces and quantum rules resist simple collapse. The images are often compared to lasagna or spaghetti, but nothing about the environment is domestic. The crust itself may be only a thin part of the whole object. Beneath it lies the core, and the core is where the real uncertainty begins. There, most of the matter is likely neutrons, packed with some protons, electrons, and possibly other particles depending on depth and pressure. It is not a normal fluid, not a solid in the familiar sense, and not a gas. It is matter at nuclear density, held in bulk by gravity. This is one of the reasons neutron stars matter so much to physics. They are not just objects in space. They are places where matter exists in a state that cannot be made and held inside a laboratory on Earth. Particle accelerators can create extreme collisions for tiny moments. Heavy ion experiments can briefly recreate hot, dense conditions. But a neutron star holds cold, dense matter under gravity for thousands, millions, and sometimes billions of years. It is a long experiment performed by the universe. The outer size of the star is one of the few clues available. If a neutron star has a certain mass and a certain radius, those two measurements reveal something about how matter behaves inside. A star with very compressible matter would be smaller. A star with matter that resists compression more strongly would be larger. This relation between pressure and density is called the equation of state. The phrase is plain, but the question behind it is deep. How does matter push back when gravity squeezes it almost as far as it can go without forming a black hole? The answer is not fully known. A neutron star cannot be opened. No probe can land on it, and no sample can be lifted from its surface. Most of what is known comes from light, timing, X-rays, gravitational effects, and the behavior of systems where neutron stars orbit other objects. Observatories do not see the interior directly. They read the outside and infer the hidden structure. Near the surface, light does not simply leave in straight lines as it would in a weak gravitational field. The star bends the paths of photons. Regions on the far side can become partly visible because the light curves around the star before traveling outward. The object shows more of itself than a normal sphere would. Gravity acts like a lens, widening the visible surface and softening the boundary between the near side and the hidden side. This means even seeing the star is an act of interpretation. A neutron star may look larger than it geometrically is, not because it has grown, but because space around it has been curved. Light has been redirected. The surface is wrapped in gravity. Observations must account for this bending, for the star's spin, for its temperature, for the pattern of hot regions, and for the composition of any thin atmosphere that may cling to it. Every measurement is connected to several hidden assumptions. Still, the measurements have improved. X-ray timing allows astronomers to study small, hot regions as the star rotates. Their changing brightness carries information about mass, radius, and the bending of light around the surface. The city-sized sun becomes a measuring instrument. Its smallness is not just a detail, it is central to everything that follows. Because so much mass is packed into such a small volume, the gravitational field near the surface is intense. The escape velocity, the speed needed to leave the star, can be a large fraction of the speed of light. This does not mean the star is a black hole. Light can still escape, but it leaves changed, stretched toward lower energy by the climb out of gravity. That stretching is called gravitational redshift. Light emitted from the surface begins with one energy and arrives far away with less. Its wavelength has been lengthened by the star's gravity. In a gentle field, the effect is small. Near a neutron star, it can become large enough to matter deeply. The light carries the memory of the gravity it escaped. The star also carries the memory of its birth and its spin. Some neutron stars rotate slowly, once every few seconds. Others rotate many times a second. The fastest known examples spin hundreds of times each second, their surfaces moving at a significant fraction of light speed. A body this dense and this small can rotate so quickly because it is held together by gravity far stronger than ordinary material strength. It is not a loose collection of rock or gas. It is compact matter bound by the collapse that made it. The rotation can slightly flatten the star at the equator. It can affect the pattern of light seen from far away. It can influence the magnetic field. In some cases, it produces the regular pulses that reveal a pulsar. But before the pulse becomes part of the story, the spin itself is worth holding in silence. A dead stellar core, wider than a city and heavier than the sun, turns in the dark with a precision that can last across ages. The magnetic field may emerge from its poles in a pattern tilted away from the rotation axis. If that field channels charged particles and radiation outward, the star can send narrow beams through space. But even without focusing on the beam, the existence of the field changes the region around the star. Charged particles move along field lines. Radiation is shaped by them. In stronger cases, the field begins to influence the crust itself, storing stress that may later be released. The density affects every familiar word: surface, atmosphere, mountain, ocean, core. These words can still be used, but they must be used carefully. An atmosphere around a neutron star, if present, may be only a very thin layer, compressed by gravity. A mountain may be measured in centimeters or less. A crust may be thin compared with the radius, yet strong enough to hold enormous strain. An ocean, in some models, may mean a layer of dense plasma or exotic matter, not water. The object invites earthly comparisons and then defeats them. A city-sized sun is not a smaller version of the sun. It is not bright in the same way, not powered in the same way, not structured in the same way. The sun is mostly hot, plasma held in a broad sphere, producing energy through fusion at its core. A neutron star is a compact remnant where fusion has ended and gravity has already done nearly all the work it can do without creating an event horizon. The sun shines because it is burning. The neutron star glows because it was crushed, and because the heat of that crushing has not yet fully escaped. This difference changes the feeling of time around the object. A normal star lives by steady production. A neutron star lives after production has stopped. It is an afterimage of a violent event, but one that can remain for immense spans. Its cooling slows. Its spin changes gradually. Its magnetic field evolves. Nothing about it is alive, but many of its properties are still moving, still shifting, still being written across time. The crust may crack. The magnetic field may twist. The star may lose rotational energy. If it is part of a binary system, it may pull material from a companion. If matter falls onto its surface, it can release X-rays as gravitational energy becomes heat. In some systems, accretion can spin the neutron star faster, recycling an old star into a millisecond pulsar. The small remnant can have more than one life after death. Yet in isolation, it may simply turn and cool. The silence of such an object is not emptiness. It is the silence of something too dense to behave like familiar matter, too small to look like a star, and too massive to be treated like a planet. A neutron star is suspended between categories. It is a stellar remnant, but not a black hole. It is made of matter, but matter altered by pressure. It is visible only through clues, but those clues can be measured with great care. The size remains the most haunting part because it is so easy to state and so hard to absorb. A sphere no wider than a city can outweigh the sun. The statement sits quietly, but it bends every other idea around it. Gravity, light, time, surface, and motion all become different because of that single compression. From far away, the neutron star may be no more than a point, or not even visible at all. It may reveal itself through X-rays, through a radio pulse, through the motion of a companion star, or through the remnant of the explosion that created it. But the hidden body is there. Small, heavy, exact. A sun's worth of mass folded down into a dark sphere, holding its shape against gravity, by forces that belong to the deepest rules of matter. This is the second step in the journey. The dying star has already collapsed. The remnant has already formed. Now the scale has changed from stellar fire to compressed matter, from brightness to density, from a giant shining body to a city-sized object, with the gravity of something much larger. The next change is quieter still. Around that dense little sphere, space itself is shaped differently, and where space bends deeply enough, time no longer keeps the same rhythm everywhere. Gravity around a neutron star does not only pull matter inward, it changes the shape of the space around the star. And because space and time are part of the same fabric, it changes the rhythm of time as well. This is where the small remnant becomes stranger than its size suggests. A city-sized object, dark or dim in ordinary light, can make the path of light curve and the pace of clocks differ from place to place. Far from such a star, space can feel almost flat. A distant clock, floating far beyond the strongest part of the gravitational field, keeps time in a way that seems ordinary. Its seconds follow one another evenly. Light moves through the surrounding dark without being forced into a sharp curve. The neutron star is still there, but its influence has thinned with distance, spreading outward into a gentler shape. Closer in, the geometry changes. The mass of the neutron star presses into spacetime. This is not a dent in a surface, because spacetime is not a sheet floating inside a larger room. It is the structure in which distance and duration are measured. A massive object changes that structure. Paths that would be straight in weaker gravity become curved. Light, which always follows the straightest available path through spacetime, bends around the star because the meaning of straight has changed. This is one of the quiet lessons of relativity. Gravity is not only a force pulling objects across space, it is also the shape of space and time themselves. A planet follows the sun because spacetime around the sun is curved. A moon follows a planet for the same reason. Near a neutron star, the curve becomes much sharper because so much mass has been compressed into so little volume. The result is not the same as a black hole. Light can still escape from the surface of a neutron star. Signals can still travel outward. The star can still be seen. But every signal leaving it has to climb through a deep gravitational field, and that climb changes the signal. Light loses energy as it rises away from the star. Its wavelength stretches. Its color shifts toward the red. The escaping light carries a trace of the gravity it has crossed. This gravitational redshift is one of the ways the star writes its mass into its light. A photon born near the surface begins its journey with a certain energy. As it travels outward, it does not slow down in the ordinary sense. Light still moves at the speed of light, but the energy measured by a distant observer is lower. The wave has been stretched by the geometry it moved through. Near Earth, this kind of effect exists, but it is tiny. Near a neutron star, it becomes part of the basic appearance of the object. Time changes in a related way. A clock close to a massive body does not tick at the same rate as a clock far away. Both clocks behave normally in their own locations. There is no local feeling of delay. No gear moves reluctantly. No atom vibrates with awareness of being slowed. But when the two clocks are compared from different gravitational depths, their rhythms do not match. This is gravitational time dilation. It can be measured even near Earth. A clock at sea level runs very slightly slower than a clock higher up, because the lower clock sits deeper in Earth's gravitational field. The difference is small, but real. Precision instruments can detect it. Satellite navigation systems must account for related effects of gravity and motion, or their positions would drift. Time is not a universal river flowing at one identical rate everywhere. It is local. It belongs to the shape of spacetime around it. Near a neutron star, the difference is no longer delicate. A clock resting close to the surface would tick more slowly compared with a clock far away in deep space. The clock itself would not feel damaged. Its mechanism would continue. Atoms would still transition between energy states. Any process occurring beside it would follow the same local rhythm. Only comparison reveals the change. From far away, the near clock appears slowed. From near the star, the far clock appears to move through a wider, higher region of time. This does not mean time has stopped. It means time has depth. The idea is easier to feel through light. Imagine not a person standing there, but a flash emitted from the surface. The flash begins close to the star, where gravity is strong and time runs slower relative to distant space. It climbs outward. Its wavelength stretches. Its energy lowers. By the time it reaches a telescope far away, the flash has been altered. The star has not merely sent light. It has sent light shaped by the gravity it escaped. The same gravity bends the path of that light. A normal sphere hides its far side. Only the hemisphere facing the observer is visible. A neutron star is different. Because its gravity curves light strongly, photons from regions beyond the apparent edge can bend around and still reach a distant telescope. More than half of the surface may be visible at once. The star shows part of its far side, not because it is transparent, but because space-time around it has turned the light. The boundary of the star becomes less simple. A hot spot on the surface may rotate out of direct view and still not vanish immediately. Its light can curve around the star. As the neutron star spins, the brightness rising and falling in X-rays carries information about the object's compactness. The pattern depends on mass, radius, rotation, and the bending of light. Astronomers read those changes carefully because the pulse of light is also a map of gravity. The surface itself may appear distorted. It is not distorted in its own frame, where the star remains a compact sphere or a slightly flattened rotating one. The distortion belongs to the observer's view. Gravity acts between the surface and the telescope, curving paths and stretching energy. Nothing has to be imagined beyond physics. The object is simply massive enough that the route taken by light is no longer the route expected in gentler space. This is why neutron stars are useful for testing gravity. They are not as final as black holes because they still have surfaces. They are not as mild as planets or ordinary stars Because their gravity is far stronger at their edges. They occupy a narrow and valuable region between the familiar and the unreachable. Their light can escape, but not without being changed. Their surfaces can be seen, but not without geometry intervening. A black hole hides its interior behind an event horizon. A neutron star exposes a surface while still bending spacetime strongly enough to bring relativity into view. There is a calm strangeness in that. The neutron star does not need to do anything dramatic to change time. It only needs to exist. Its mass, packed tightly into a small radius, sets the geometry around it. A clock closer in follows that geometry. A photon leaving the surface follows that geometry. Matter falling toward it follows that geometry. The star's gravity is not an added effect, but the condition under which everything nearby moves. If gas from a companion star falls toward a neutron star, the journey inward releases enormous energy. The gas spirals down through an accretion disk, heating as it loses gravitational potential energy. Close to the surface, it may glow in X-rays before striking the star. The energy released by a small amount of falling matter can be far greater than the energy released by ordinary chemical burning. Gravity is doing the work, converting height in a curved space-time into heat and radiation. This too is part of time's story. The closer matter gets, the deeper it moves into the gravitational well. Its motion speeds up, its light changes. Processes near the surface become shifted when measured from far away. An accreting neutron star can appear as a bright X-ray source, not because it is fusing matter like a normal star, but because the fall itself has become a power source. The surface is the stopping place that a black hole does not have. Matter falling onto a black hole crosses the event horizon and disappears from view. Matter falling onto a neutron star can strike a material surface. That impact can heat the surface. It can create bursts. It can reveal the size and gravity of the star through the light released. The presence of a surface makes the neutron star observable in ways that a black hole is not. Yet the surface is not gentle. The energy of impact is shaped by the same compactness that slows time. Gravity has gathered the falling matter into a final rush. When it arrives with the stored energy of the climb it has lost. The star receives it without softness. In some neutron star systems, X-ray bursts occur when material from a companion accumulates on the surface. Hydrogen or helium can build up under the star's gravity until nuclear burning ignites suddenly across the layer. These bursts are not the same as the core fusion of a living star. They are surface events, brief flashes, on a remnant that no longer supports itself by fusion. The light rises and fades, carrying information about gravity, composition, and the compact surface beneath. Even in these brighter systems, the deeper story remains slow. Space-time is curved, time is local. Light is altered by escape. The star's small size makes every effect stronger, because the surface lies so close to the mass. If the same mass were spread out across a much larger star, the surface gravity would be weaker. The clock at the edge would not be slowed as much. The light would not be redshifted as strongly. Compression makes relativity visible. This is one of the great reversals of scale. A smaller star can make a stronger gravitational environment than a larger one if the mass is packed tightly enough. Size alone does not decide gravity's intensity at the surface. Compactness does. A neutron star is compact enough to make the edge of the object a place where the ordinary intuition of space begins to fail. The sky near such a star would not look like a quiet dome. Light from the surrounding universe would be bent. The star's own surface could be visible in a distorted way. Distant starlight passing close to the neutron star would curve, shifted from the path it would take in empty space. The object would act as a lens, though far smaller than the gravitational lenses made by galaxies and galaxy clusters. The principle is the same. Mass tells light how to travel. Time follows the same instruction. A clock far away and a clock near the neutron star are both honest. Each measures time properly in its own place. The difference appears when the two are brought into relation, when signals pass between them, when light leaves one region and arrives in another. The universe does not keep a single master clock above all places. It keeps local clocks, each one tied to motion and gravity. For a neutron star, the local clock near the surface is slowed compared with the distant one. The exact amount depends on the mass and radius of the star. A more compact neutron star produces a stronger effect. This is one reason mass and radius matter so much. They are not only measurements of size and weight, they define the curvature around the object and the rhythm of time near it. The question of time near neutron stars is sometimes described in exaggerated language, as if these objects freeze reality. They do not. That belongs more closely to the idea of an event horizon, and even there, the full story depends on perspective. A neutron star slows time relative to distant space, but it remains outside the boundary that would prevent light from escaping. It is extreme, but not final. That distinction is important. It leaves room for observation. It allows light, X-rays, radio pulses, and sometimes matter to carry information outward. It makes the neutron star a place where relativity can be studied rather than only inferred from absence. The object is dark in one sense, but not hidden completely. It speaks through altered signals. The signals arrive after crossing distance and curvature. A pulse may be delayed, a spectrum may be shifted, a brightness pattern may be smoothed by light bending. A burst may fade in a way that reveals the pull of the surface. Each observation is a small message from a region where gravity is strong enough to reshape time, but not strong enough to close the universe behind a horizon. There is no need to imagine nor even thinking of lay. The physics is already enough. A compact star turns in darkness. Light climbs away from it. Clocks near it fall behind. Clocks far away. The surrounding space bends the paths of photons, revealing parts of the surface that should have been hidden. Gravity holds the object together and changes the rhythm of events around it. The dying star became a city-sized sun. The city-sized sun bends space-time, and in that bending, time becomes less like a single river and more like a landscape, lower near the star, higher far away, continuous but not level. This is where the next form of neutron star begins to matter. If the compact remnant spins and sends a beam across space, its rhythm can be measured from far away. The pulse may arrive again and again, steady as a clock, shaped by rotation, magnetism, and gravity. A dead star can become one of the most precise timekeepers in the cosmos. A neutron star can be nearly invisible in ordinary light and still announce itself across the galaxy with extraordinary precision. The announcement does not come as a voice, or a flare that fills the sky, or a steady glow like a living star. It comes as a pulse. A narrow beam sweeps through space, misses, returns, misses again, and then crosses the line of sight of a distant telescope. For a brief moment, the dead star is heard as a rhythm. This is a pulsar. The name comes from the pulses that arrive at Earth, but the object itself is still a neutron star. It is compact, dense, and strongly magnetized. It spins. Around its magnetic poles, particles are accelerated, and radiation escapes in beams. If the magnetic axis is tilted away from the spin axis, those beams sweep around as the star rotates. When one of them points toward Earth, a telescope records a flash. When it turns away, the flash fades. The star has not stopped shining. Its beam has simply moved on. The image is often compared with a lighthouse, and the comparison is useful if it is kept simple. A lighthouse does not flash because its lamp turns on and off. It flashes because a beam rotates across the horizon. A pulsar can work in a similar way. Its emission may be continuous along the beam, but from far away it appears as a series of repeated pulses, one for each rotation, if the beam crosses the observer's direction. Light, silence. Light, silence. That rhythm can be very slow, or it can be faster than any mechanical clock. Some pulsars rotate once every few seconds. Others rotate many times each second. Millisecond pulsars, the fastest class, can spin hundreds of times in a single second. their signals arriving with a regularity that can rival some of the best timekeeping methods built on Earth. The body producing this rhythm is not a delicate instrument. It is a collapsed stellar core, wider than a city, heavier than the sun, turning in space with astonishing steadiness. The steadiness comes from the nature of the object. A neutron star is small and dense, so it can rotate quickly without tearing itself apart in the way ordinary matter might. Its enormous gravity holds it together. Its mass is packed close to the rotation axis, and its moment of inertia is stable over long periods unless something disturbs it. It is not perfectly constant. Pulsars slow down over time as they lose rotational energy, but the slowing can be measured with such care that the pulse becomes a clock with a very long hand. At first, the discovery of pulsars seemed strange enough that the signals invited every kind of speculation. The pulses arrived too regularly to be dismissed as random noise. They were not like ordinary variable stars, and they did not drift like nearby interference. The first known pulsar sent radio pulses at a steady interval, again and again, from the same region of the sky. The regularity was the mystery. Nature had placed a metronome in deep space. The answer was not an artificial transmitter. It was a rotating neutron star. That answer did not make the object less strange. It made it better. A dead star, formed from collapse, could spin and send a beam across light years with the patience of a signal fire. The pulse that arrives at a radio telescope may have traveled through interstellar gas, through magnetic fields, through years or centuries of empty space, and still it preserves the timing of a small rotating sphere no telescope can see as a surface. The pulse carries more than timing. It carries information about the space it crossed. Radio waves at different frequencies can arrive at slightly different times because free electrons between the stars slow lower-frequency radio waves more than higher-frequency ones. This effect is called dispersion. By measuring the delay, astronomers can estimate how much ionized material lies between Earth and the pulsar. The dead star becomes a probe, sending a signal through the thin matter of the galaxy. In that way, pulsars are not only clocks, they are lanterns placed behind the mist. The beam does not travel through a perfect vacuum. The galaxy contains gas, dust, plasma, and magnetic fields. Most of it is so thin that it would feel like emptiness by any earthly standard. But over thousands of light years, even a thin medium leaves fingerprints. Pulsar signals can be delayed, scattered, polarized, and slightly distorted. Each change reveals something about the invisible material between the source and the observer. The pulse begins near a surface where gravity bends light and time runs slower than in distant space. It then crosses the magnetosphere, the region around the neutron star controlled by its magnetic field. There, charged particles move along magnetic field lines and radiate. The exact process by which pulsar beams are produced is still an area of research. The broad picture is clear enough. Rotation, magnetic fields, and charged particles work together to create beams that sweep across the cosmos. The details remain unfinished. That unfinished part is not a weakness in the story. It is part of the value of pulsars. They are measured with high precision, yet their emission mechanisms still contain open questions. Different wavelengths can come from different regions around the star. Radio pulses, X-rays, and gamma rays may trace different particle populations and magnetic structures. The same compact remnant can speak in several kinds of light, each one carrying a different view of the environment around it. A pulsar loses energy as it spins. Slowly, almost imperceptibly, its rotation rate decreases. The beams continue to sweep, but the interval between pulses lengthens by a tiny amount. Over one day, the change may be small. Over years, it can be tracked. The star is spending its rotational energy, pouring it into radiation, particle winds, and the surrounding nebula. A pulsar is not powered by fusion. It is powered by the rotation left behind after collapse. Some young pulsars sit inside glowing supernova remnants. The Crab pulsar is one of the best-known examples. At the center of the Crab Nebula, A neutron star spins roughly 30 times each second, energizing the surrounding cloud with a wind of particles. The nebula glows across many wavelengths. Filaments spread outward from an explosion seen on Earth almost 1,000 years ago. At the center, the remnant still turns, still feeding the cloud with energy from its rotation. The image is not loud, if held in the right way. A faint nebula expands. A small star at its center spins. Particles flow outward. The dead star's pulse keeps time inside the remains of its own birth. Not all pulsars are young. Some are old and have been spun up again. In binary systems, a neutron star can pull material from a companion. As that material spirals inward, it can transfer angular momentum to the neutron star, making it rotate faster. Over long spans, the old remnant becomes a millisecond pulsar. This process is sometimes called recycling. The name is plain, but the idea is elegant. A dead star receives matter from a companion and is turned into a faster clock. Millisecond pulsars can be especially stable. Their pulses arrive so regularly that an array of such pulsars spread across the sky can be used to search for very low-frequency gravitational waves. The idea is patient. If spacetime itself is being stretched and squeezed by waves passing through the galaxy, the arrival times of pulses from many distant pulsars may shift in a correlated way. Each pulsar becomes part of a galaxy-sized detector, with Earth at one end and the pulsars as timekeeping points across space. This is a different kind of observatory. It does not have one mirror or one antenna. It uses the galaxy itself. The clocks are neutron stars. The signals are radio pulses. The distances are measured in light years. The waves being searched for may come from pairs of supermassive black holes orbiting one another across the universe. A small dead star can help measure motions among the largest dark objects known. The scale turns inside out. A compact remnant no wider than a city becomes part of a structure as wide as the Milky Way. Its pulse leaves the star, crosses interstellar space, reaches Earth, and joins the timing of other pulsars in a pattern that may reveal a slow trembling of spacetime. The neutron star is small, but its use is not small. Its regularity gives astronomers a way to notice changes too subtle for ordinary instruments. The stability of a pulsar is never absolute. Some pulsars glitch. A glitch is a sudden small change in rotation, usually a spin-up, as if the star has adjusted itself from within. The cause is thought to involve the interior, perhaps the interaction between the solid crust and a neutron superfluid beneath it. The outer crust and the interior may not rotate in perfect unison at all times. Stress can build. Then the star's rotation shifts. A glitch is a brief event, but it points downward. It suggests that the pulse measured from Earth is connected to the hidden structure of the star. The beam comes from the magnetosphere, but the rotation belongs to the whole object. If the interior changes how it shares angular momentum with the crust, the clock changes. A tiny jump in timing becomes a clue about matter that cannot be seen, touched, or recreated in a laboratory. The pulse is not only a lighthouse beam, it is a record of the star's deep interior. Some pulsars also show timing noise, small irregularities in their rotation over time. The clock is good, but not perfectly smooth. Magnetic fields evolve. Particles escape. The crust may shift. The star's environment may change. In binary systems, orbital motion adds further patterns. A pulsar must be understood not as a simple machine, but as a compact physical world with layers, stresses, fields, and histories. Even so, the pulse remains one of the most orderly signals in astronomy. It can be folded, measured, compared, and used to test gravity. In systems where a pulsar orbits another dense object, the timing of the pulses can reveal relativistic effects. Orbits can shrink. Light travel time can change. The pulse arrives early or late by tiny amounts, and those differences become evidence for the bending of spacetime, the loss of energy, or the presence of an unseen companion. One of the most important binary pulsars, showed that two neutron stars orbiting each other were losing energy in exactly the way expected if they were emitting gravitational waves. Long before direct detectors measured those waves on Earth, pulsar timing had already revealed their effect indirectly. The orbits slowly tightened. The timing changed. The dead stars were speaking through mathematics and radio pulses, not through visible drama. This is the deeper calm of pulsars. They turn catastrophe into rhythm. A supernova makes the neutron star. Collapse compresses the core. Rotation speeds up. Magnetic fields intensify. Then, after the violence has passed, the remnant becomes regular. It sends a beam into the dark, not once, but again and again, for thousands or millions of years. The pulse is the afterlife of collapse. There is also a kind of selection hidden in every pulsar observation. Many neutron stars may beam in directions that never cross Earth. Their lighthouses turn, but their light sweeps elsewhere. They may be just as active, just as regular, and yet remain unseen from this planet. The known pulsars are not all the pulsars that exist. They are the ones whose beams happen to pass through the small region of space where Earth is moving. The galaxy may be filled with silent clocks from this point of view, clocks whose hands never point here. A pulse that does reach Earth may be faint. It can be buried in noise, hidden among human-made radio signals, or spread across frequency by interstellar plasma. Detecting it requires patience. Radio telescopes gather the signal. Computers search for repeating patterns. A pulse too weak to see once can become clear when many rotations are stacked together. The star has been sending the rhythm all along. The observer has to learn how to listen. Listening to pulsars is not listening in the human sense. Radio waves are converted into data, then into plots, timing models, and sometimes into sound for demonstration. But beneath the conversion is a real periodic signal from a rotating compact star. It is not music. It is rotation made visible through radiation. It is the steady sweep of a beam from a remnant that formed when a massive star's core fell inward. The lighthouse image returns, but softer now. Not a tower on a coast, not a lamp cutting through rain, but a dense sphere in interstellar dark. Its magnetic poles are tilted. Its beams sweep through space. Most of the time, nothing happens at Earth. Then the beam crosses the line of sight, and a radio telescope receives a pulse. A fraction of a second later, or a few seconds later, it comes again. The rhythm can continue through the night, through the year, through decades of observation. Each arrival is compared with the predicted arrival. Each tiny difference is kept. Over time, the pulsar becomes both a clock and a question. It measures time, and it reveals all the ways time is affected by motion, gravity, plasma, companions, waves, and the hidden structure of the star itself. A neutron star began as the collapsed core of a massive sun. In a pulsar, that collapse has left behind not only density, but timing. The object is small enough to curve spacetime sharply, dense enough to hold itself against gravity, magnetic enough to guide particles into beams, and steady enough to mark the passing of years across the galaxy. The pulse fades from the telescope. The star turns again. Space remains dark between one sweep and the next. Then the beam returns, carrying with it the memory of rotation, gravity, and a dead star that has become one of the universe's quietest clocks. Magnetism is invisible until matter begins to answer it. Around Earth, it turns a compass needle and guides charged particles toward the polar sky, where auroras can spread in green and red curtains above the atmosphere. Around a neutron star, the same basic force is carried into a place where ordinary scale has ended. The magnetic field is not a small influence added to the star. It can shape the space around it, guide radiation, stress the crust, and turn a compact remnant into one of the most magnetic objects known. A neutron star inherits part of its magnetic life from the star that made it. Before collapse, the massive star may have contained magnetic fields threaded through its hot plasma. Those fields were spread through a large volume. When the core collapsed, The volume shrank violently. The field was compressed along with the matter. What had once filled a stellar core was forced into a sphere no wider than a city. Compression changes everything. The field lines close around the neutron star in patterns that may be simple in outline and difficult in detail. Near the magnetic poles, charged particles can be accelerated outward. Around the star, plasma is trapped and guided by magnetic structure. Radiation may escape in beams. The magnetic field, the rotation, and the dense surface all become linked, each one affecting the others. For many neutron stars, the field is already stronger than anything familiar on Earth. For magnetars, it becomes stronger still. A magnetar is a neutron star whose magnetic field dominates much of its visible behavior. It may rotate more slowly than some pulsars, but its field carries an enormous store of energy. That energy can twist, stress, and sometimes break the star's outer layers. It can rearrange the surrounding magnetosphere. It can release bursts of X-rays and gamma rays that cross space from a body smaller than many cities. The word burst can sound sudden, but the deeper process is slower. Magnetic stress builds over time. The crust of the neutron star, rigid and compressed, is tied to field lines that may shift and twist. The star is not a loose sphere of gas. It has a crust strong beyond ordinary materials, yet not free from strain. Under the pull of magnetic forces and the movement of the field, that crust can deform. It can hold tension. Then, it can give way. A starquake may occur. The name is borrowed from earthquakes, but the comparison is limited. On Earth, plates move over a hot interior, rock breaks, and waves travel through the ground. On a magnetar, the crust is a thin shell of dense nuclear material wrapped around a far stranger interior. When magnetic stresses shift it, the released energy can travel through the star and into the magnetosphere. The surface may move by a small amount, but in that environment, a small movement can carry immense energy. The magnetosphere answers. Charged particles spiral along magnetic fields. Radiation changes. A sudden rearrangement can create a flare. Most flares are small by magnetar standards, though still powerful compared with common stellar events. Rare giant flares are different. They can release as much energy in a short time as the sun releases over long periods. The brightest known magnetar flares have affected instruments in Earth orbit, even from many light-years away. A small remnant, almost lost in the galaxy, can still disturb detectors near this planet when its magnetic field shifts. The event does not need to be described loudly. The facts are enough. A dark, compact star, distant and unseen by the eye, adjusts its magnetic structure. A pulse of high-energy light leaves it. Years later, after crossing the galaxy, that light touches machines near Earth. The field itself is hard to picture because it has no color. Diagrams show magnetic lines as curves, looping from pole to pole, but those lines are a way of drawing direction and strength. Space around the magnetar is not filled with glowing wires. It is filled with a condition. Charged particles feel that condition. Photons moving through such fields may behave differently from photons in weaker environments. The empty region around the star is not empty in the usual sense. It is organized by magnetism. In the strongest fields, even the vacuum becomes part of the story. Quantum physics predicts that empty space, when placed in a strong enough magnetic field, can affect the polarization of light passing through it. Polarization is the orientation of a light wave's vibration. Around a magnetar, the magnetic field may influence that orientation, turning the vacuum into something that behaves almost like a material medium. The phrase often used is vacuum birefringence. The idea is quiet and strange. Emptiness itself responds to the field. This is not science fiction. It is a prediction of quantum electrodynamics, the theory describing how light and charged particles interact. Magnetars give astronomers a natural setting where such effects may become visible. On Earth, laboratory fields are far weaker. Around a magnetar, Nature has built a place where the vacuum can be tested under conditions no human machine can maintain. The magnetic field also changes the way atoms behave near the surface. In ordinary conditions, atoms have shapes and energy levels determined by electric forces between nuclei and electrons. In a magnetar's field, those electron orbits can be squeezed and stretched. Atoms may become elongated along the magnetic direction. Chemistry, in any familiar sense, becomes a poor guide. Matter is still matter, but the rules that shape it are being pushed into a very narrow and unusual regime. The surface may hold hot regions where magnetic field lines guide returning particles downward. These regions can glow in X-rays. As the magnetar rotates, the hot regions move in and out of view, producing changes in brightness. Gravity bends the light from the surface. The magnetic field shapes the emission before it escapes. The final signal reaching a telescope carries both stories at once: the curve of spacetime and the structure of magnetism. There is no clean separation between these forces near a neutron star. Gravity makes the object compact. Compactness makes the surface field intense. Rotation moves the field through surrounding plasma. The field shapes the radiation. The radiation reveals the star. Each piece leans on the others. A magnetar is often born from the same general pathway as other neutron stars, but not every neutron star becomes one. The exact origin of magnetar strength fields is still studied. Some models suggest that a very rapidly rotating newborn neutron star can amplify its magnetic field through turbulent motion in the first moments after collapse. Other ideas involve inherited magnetic fields from the massive star before it died. The honest answer is that more than one pathway may be possible, and the full story is not settled. That uncertainty matters because magnetars do not behave like simple older pulsars. Their rotation often slows quickly because the strong magnetic field drains rotational energy. Their bursts and flares suggest that magnetic energy, not rotation alone, powers much of what is seen. A normal rotation-powered pulsar spends its spin. A magnetar spends its magnetic field. Slowly, the field evolves. It may decay over thousands of years. As it changes, it can heat the crust, drive activity, and alter the surrounding magnetosphere. Some magnetars are bright in X-rays even when they are not flaring, likely because magnetic energy continues to warm the surface or outer layers. They are not burning through fusion. They are not shining like young suns. They glow because magnetic stress and dense matter are exchanging energy in a compact remnant. There is a hidden softness in the word decay. It can make the process feel passive, as if the field simply fades, but magnetic decay inside a neutron star can be active. Currents move through dense matter. Heat is produced. Stress shifts through the crust. The star's outer layers respond to changes below and above them. A magnetar may seem quiet for years, then change suddenly, not because it has awakened, but because stored magnetic energy has found a new path outward. The crust is central to this. It is thin compared with the radius of the star, but it is the layer that can hold strain. Beneath it, the core may include superfluid neutrons and superconducting protons, depending on the conditions inside. These states of matter can interact with magnetic fields in ways still being studied. The interior is not directly visible. Magnetar activity may be one of the few ways the hidden interior leaves marks on the outside. A flare is therefore not only an outburst, it is a clue. The timing, energy, and spectrum of magnetar bursts can reveal how the magnetic field is arranged, how the crust responds, and how energy travels through the magnetosphere. Some bursts last fractions of a second. Some activity continues in tails that pulse with the star's rotation. A giant flare may begin with a sharp spike of high-energy radiation, followed by a fading signal shaped by the rotating star. Even the fading carries structure. The magnetar turns as the trapped fire cools. In such events, the pulse after the initial flare can reveal the rotation period. The light rises and falls as the star spins, as if the burst has painted the magnetic structure with heat, and the rotation brings different parts into view. A small object hidden across the galaxy, becomes briefly readable. Its spin, field, and surface all imprint themselves on the afterglow. Magnetars also connect to one of the newer questions in transient astronomy. Fast radio bursts, brief flashes of radio energy from far beyond the Milky Way, were mysterious for years. Then a magnetar in this galaxy produced a radio burst with similarities to the weaker end of the fast radio burst population. This did not solve every fast radio burst, and it did not mean all of them come from magnetars in the same way, but it gave a firm link between at least some intense radio flashes and magnetar activity. The connection is valuable because magnetars can produce sudden magnetic rearrangements, particle acceleration, and high-energy radiation. They are natural candidates for events that release short, bright signals. Yet the details remain open. Some fast radio bursts repeat, some do not appear to. Some live in active environments far outside this galaxy. Magnetars may be part of the answer, perhaps a large part. But the universe has not made. The magnetar keeps its mystery without needing to become a monster. It is a neutron star with a magnetic field strong enough to reshape matter, radiation, and perhaps even the behavior of empty space. It can crack its own crust. It can send high-energy light across the galaxy. It may help explain some of the shortest radio flashes ever found. But it is still a remnant. It is still the compressed core of a dead star, turning in the dark, cooling, evolving, and slowly spending the energy stored in its field. Compared with a pulsar, a magnetar feels less like a clock and more like a wound under tension. The pulse may still be there, but it is not the whole identity of the object. The magnetic field is the main presence. It threads through the crust. It surrounds the star. It stores energy that cannot remain arranged forever. When the arrangement shifts, the star gives off light. This light is often too energetic for human eyes. X-rays and gamma rays belong to a part of the spectrum that must be caught by instruments above the atmosphere or by detectors made for high-energy photons. The eye would not see the magnetar as a blazing object in the night. The signals that reveal it are translated through machines, through data, through repeated measurements. The object is not hidden because it is absent. It is hidden because the universe speaks in more wavelengths than sight can hold. The magnetic field is one way the star's history remains unfinished. The supernova has passed. The debris has spread outward. The core has settled into its compact form, but inside and around the remnant, energy is still stored in hidden arrangements. Currents still move. Fields still twist. The crust still holds stress. The star is dead only in the sense that fusion has ended. In other ways, it continues to change. Far from the magnetar, space looks calm. Starlight crosses it. Gas drifts. Dust cools. Then, from one small point, a burst arrives. It may last less than a blink, but it began in a place where magnetism overruled the ordinary behavior of matter. It began with a compact star whose field is strong enough to make even emptiness answer. Afterward, the darkness returns. The beam fades. The X-rays lessen. The magnetar continues to turn, carrying its field through the surrounding space like an invisible weather system wrapped tightly around a dead sun. No human eye sees the field lines. No surface shows them as glowing curves. But charged particles know them. Light knows them. The crust knows them. And slowly, beneath that invisible pressure, the star waits for the next adjustment. Inside a neutron star, the word inside becomes difficult. On Earth, the interior of an object usually means a place that can be reached by cutting, drilling, melting, or breaking. The inside of a stone can be exposed. The inside of a planet can be inferred from waves and fields. But a neutron star keeps its deepest layers behind a surface no material probe could cross, beneath gravity strong enough to make ordinary exploration meaningless. The only way inward is through physics. The outermost layers may be thin, hot, and strongly affected by magnetic fields. If the star has a light atmosphere, perhaps made of hydrogen or helium in some cases, that atmosphere is compressed into a layer far thinner than any atmosphere on Earth. Gravity presses it close to the surface. Radiation leaving it carries information about temperature, composition, and curvature, but not easily. The signal has already been shaped by the star before it begins the long journey outward. Beneath that thin outer skin lies the crust. The crust is not rock. It is not metal in the ordinary sense. It is a lattice of atomic nuclei and electrons forced together under pressure that increases with every step downward. Near the top, the nuclei may still resemble atoms, though squeezed and stripped of normal freedom. Deeper down, the nuclei grow heavier and richer in neutrons. Matter is being held at the edge of stability because the pressure permits arrangements that would fall apart almost instantly in empty space. The deeper crust is stranger still. At a certain density, nuclei cannot hold all of their neutrons. Some neutrons become free, not free in open space, but free to move through the dense background of the crust. This is called neutron drip. The phrase is small, almost gentle. The reality is a transition in the identity of matter. The star has moved below the level where ordinary nuclei can keep their familiar borders. Free neutrons seep through the lattice. Electrons form a dense sea. The nuclei become crowded and distorted. The crust is solid, but it is a solid made under rules that have almost no comparison with ordinary minerals. It may be stronger than steel by enormous margins, yet it remains only a thin shell around something even less familiar below. In some models, the lower crust forms shapes called nuclear pasta. The name is borrowed from kitchens, not from space, because the mathematics can produce sheets, rods, tubes, and tangled forms that resemble lasagna or spaghetti in outline. But these are not soft strands. They are arrangements of nuclear matter, shaped by a competition between the strong nuclear force, electric repulsion, pressure, and quantum rules. The language becomes homely because the physics is too distant. A quiet irony sits there. One of the densest materials in the universe may be named after food. The nuclear pasta layer, if it exists as models suggest, may affect how the star cools, how it cracks, how it vibrates, and how it conducts heat and electricity. It may help determine whether the crust can support tiny mountains. It may influence gravitational wave emission from a slightly asymmetric spinning neutron star. Something deeply hidden, never seen directly, can still shape the signals that arrive at Earth. Below the crust begins the core, and the core is where certainty grows thinner. The outer core is usually described as a fluid of mostly neutrons, with some protons, electrons, and perhaps muons. The word fluid does not mean water-like. It means the material can flow, though under conditions that belong to nuclear density. The neutrons may form a superfluid, a state in which they move without ordinary friction. Protons may become superconducting, allowing electrical currents and magnetic structures to behave in unusual ways. These states are not fantasy. Superfluidity and superconductivity are known in laboratories under cold conditions. Inside a neutron star, they may appear in matter that is cold in one sense but unimaginably dense in another. Cold here does not mean comfortable or still. It means cold compared with the energy scales of nuclear matter after the star has aged. The temperature may be high by human standards, yet low enough for quantum states to organize the particles collectively. This is one of the hidden reversals of neutron stars. A place born in supernova heat may later contain some of the largest superfluids in the universe. If neutrons in the core form a superfluid, the rotation of that superfluid cannot behave like ordinary swirling water. It is carried in quantized vortices, tiny organized lines of rotation. These vortices may pin to structures in the crust or interact with other components of the star. When the crust and interior exchange angular momentum, a pulsar glitch can occur. A timing jump seen from Earth may be the surface trace of motion in an invisible quantum ocean. The pulse changes. The core has spoken. The inner core is less certain. Depending on the true equation of state, matter might remain mostly nucleonic, made of neutrons and protons under extreme pressure, or new particles may appear. Hyperons, particles containing strange quarks, may become energetically possible. Meson condensates have been proposed. Some models allow quark matter, in which neutrons and protons dissolve into a denser state where quarks are no longer locked inside individual particles in the usual way. Each possibility changes how the star supports itself against gravity. No one knows which answer nature has chosen. The difficulty is that the core is hidden and the pressure is beyond direct experiment. The equation of state is the rule describing how dense matter pushes back when squeezed. If the matter is stiff, it resists compression strongly, and neutron stars can be larger at a given mass. If it is soft, they compress more, and the radius becomes smaller. If a phase transition occurs deep inside, the relation between mass and radius may carry subtle signs of that change. Mass and radius become clues to matter that cannot be touched. This is why X-ray observations are so valuable. A rotating neutron star with hot spots on its surface sends light that rises and falls as the star turns. Because gravity bends the light, the shape of the pulse depends on the star's compactness. By modeling the changing X-ray brightness, astronomers can estimate the star's mass and radius. These measurements are not simple photographs. They are interpretations of light that has escaped curved spacetime. The Neutron Star Interior Composition Explorer, known as NICER, was built to make these kinds of measurements from the International Space Station. It observes X-rays from pulsars and uses their changing light to help constrain the mass-radius relation. The goal is not only to know the size of a star. The goal is to learn what dense matter is doing inside it. The method is patient. Hot regions rotate into view. Light from the far side bends around the star. The pulse shape carries information about gravity, geometry, and surface temperature. Models are compared with the data. Different possible interiors are tested. The result is not a single open door, but a narrowing corridor. Some forms of matter become less likely. Others remain possible. A neutron star becomes a laboratory without walls. Other clues come from gravitational waves. When two neutron stars orbit and merge, the way they deform each other before collision depends on how stiff their matter is. A softer star is more easily distorted by tidal forces. A stiffer star resists. Detectors on Earth can measure parts of this signal, and those measurements add another constraint to the equation of state. Light from the merger adds still more information because the amount and kind of material thrown into space depend on the structure of the stars. The interior is therefore studied from several directions at once. X-rays from rotating surfaces, radio timing from pulsars, gravitational waves from mergers, nuclear experiments on Earth, theory built from particle physics. None of these alone gives the full answer. Together, they begin to outline the dark center. The outline is still incomplete. This incompleteness is not a failure of science. It is the honest shape of the problem. Dense matter does not reveal itself easily. The strong nuclear force, which binds protons and neutrons together, behaves in complicated ways when many particles are packed at high density. Calculations become difficult. Experiments cannot simply reproduce a stable piece of neutron star core. Observations must be gathered from objects many light-years away, each with its own mass, spin, field, and history. The star keeps its interior by being far away and by being what it is. One of the deepest questions is how heavy a neutron star can become before it fails. There is a maximum mass, but the exact value depends on the equation of state. If the matter inside can support more pressure, the star can remain stable at higher mass. If not, gravity wins, and the neutron star collapses into a black hole. Observations of very massive neutron stars are therefore powerful. Each one says that the interior must be stiff enough to support at least that much weight. The heaviest measured neutron stars already rule out many soft models. They show that matter inside the core cannot give way too easily. Yet the radii suggest that the matter cannot be infinitely stiff either. It must find a narrow path, resistant enough to prevent collapse, compressible enough to fit inside a sphere only about the size of a city. The truth lies between extremes. There may be stars that are almost twins in mass, but different inside. There may be a transition to quark matter that changes the radius while leaving the mass similar. There may be no sharp transition at all, only a gradual change in how particles arrange themselves. These possibilities are still being tested. The data have improved, but the core remains partly veiled. In a sleep-dark room, this can be held as a simple image. A small star turns far away. Its surface sends X-rays. Its pulses arrive. Its gravity bends light. Beneath the surface, layer after layer of matter changes character. Atmosphere, crust, neutron drip, nuclear pasta, outer core, superfluid, perhaps stranger matter deeper still. No camera descends there. No instrument touches it. Yet every pulse carries a small piece of the answer outward. The inside of a neutron star is not only a place, it is a question compressed into matter. It asks how atoms end. It asks how nuclei behave when crowded beyond ordinary stability. It asks whether neutrons can flow without friction through a star's core. It asks whether quarks remain hidden inside particles or emerge into a wider sea. It asks how gravity and quantum physics share the same small sphere without either one fully explaining the other. The old massive star made elements through fusion. The neutron star does not continue that work in the same way. Its task, if the word can be used gently, is different. It holds matter at a boundary. It preserves conditions that the universe rarely makes and that human machines cannot sustain. It is less a furnace than a vault. The vault is not quiet because nothing happens. It is quiet because most of what happens is hidden. Heat moves slowly outward. Vortices may shift in the superfluid interior. Magnetic fields may thread through superconducting regions. The crust may strain. The core may settle into states still unnamed by direct observation. Across years, centuries, and longer spans, the star cools and spins down, while the particles inside follow rules written at densities beyond ordinary matter. From outside, the neutron star may seem like a point. From inside, if inside could be imagined without a body to be crushed there, it would be a layered world of pressure. Every deeper region removes another familiar idea. Atoms give way to nuclei. Nuclei give way to free neutrons. Neutrons may give way to collective quantum motion. Deeper still, perhaps the particles themselves may change their arrangement. The honest answer remains unfinished. Observations are narrowing it. Models are improving. The universe is giving clues through X-rays, radio pulses, gravitational waves, and the fading light of mergers. But the core has not yet been fully translated. The neutron star continues to turn, holding its secret beneath a crust thinner than its gravity makes it feel. Around it, light bends and time slows. Within it, matter waits in a form that may be ordinary nuclear matter pressed to its limit, or something stranger beginning in the dark. A neutron star can spend a long age alone, turning slowly in the dark, cooling after the violence that made it. But many neutron stars are not alone. Some are born with companions, bound in pairs by gravity, circling one another across a space that grows smaller over time. Two dense remnants can move together for millions or billions of years, each one carrying the collapsed heart of a dead star, each one bending spacetime around itself. At first, their orbit may seem stable. One star moves around the other. Or more exactly, both move around their shared center of mass. The pair may be separated by a distance far larger than either star. They are tiny objects compared with the orbit they trace, yet their gravity is strong, and their motion is not perfectly silent in the fabric of spacetime. As they circle, they give energy away in the form of gravitational waves. These waves are not sound. They do not move through air, and they do not need any material medium. They are ripples in spacetime itself, stretches and squeezes moving outward at the speed of light. Most gravitational waves are far too weak to feel. By the time they cross Earth, even waves from enormous cosmic events change distances by less than the width of an atomic nucleus across instruments built many kilometers long. The signal is small. The event is not. When two neutron stars orbit one another, the emitted gravitational waves carry energy away from the system. The orbit tightens. The stars draw closer. As the distance shrinks, they move faster. The waves grow stronger. A slow dance becomes a rapid spiral, though the word dance is almost too graceful for what is happening. These are not soft bodies turning in a room. They are compact remnants, each with more mass than the sun, moving through a deepening gravitational field. For a long time, the approach can be quiet from far away. The stars may not shine brightly in visible light. They may be difficult to find unless one is a pulsar, sending regular radio pulses that reveal the orbit. But the loss of energy is still happening. The clockwork is changing. The path is narrowing. A binary system can spend ages moving toward a final few minutes. In those final minutes, the gravitational wave signal rises in frequency and strength. The orbit becomes faster and faster. The stars circle each other many times each second. Spacetime around them is no longer shaped by one compact object alone, but by two, moving rapidly, pulling tides through each other's matter. The surfaces may deform, the crusts may strain. The outer layers may begin to feel the companion not as a distant point, but as a force changing the star's own shape. This tidal deformation is one of the most valuable parts of the signal. A neutron star is not perfectly rigid. Its matter responds to the gravity of its companion. If the interior is stiff, the star resists distortion. If the interior is softer, it stretches more easily. The gravitational waves carry a trace of that response. Before the stars even touch, their hidden interiors leave a mark on the rhythm of spacetime. Then the stars merge. There is no ordinary surface collision to compare with it. The crusts and cores meet under gravity and velocity that belong to relativistic physics. Matter is torn outward. Some material forms a hot, dense disk around the central remnant. Some is ejected into space in streams rich with neutrons. For a short time, the result may be a heavier neutron star, unstable and rapidly rotating, or it may collapse almost at once into a black hole. The outcome depends on mass, rotation, and the unknown stiffness of the matter inside. The merger is not only an ending, it is also a forge. The material thrown outward from the collision is rich in neutrons, and that matters deeply. In ordinary stars, many elements are built through fusion, but the heaviest elements require other pathways. In neutron-rich ejecta, atomic nuclei can capture neutrons rapidly, faster than they can decay. This process, called rapid neutron capture, can build heavy elements such as gold, platinum, and uranium. A collision between dead stars can create the ingredients of planets, electronics, and stone hidden deep inside worlds. The connection is quiet enough to hold for a moment. Some atoms on Earth may have begun in events like this, not in gentle starlight, not in the long main life of a star, but in a brief merger of two collapsed cores. A ring, a wire, a trace element inside rock. A grain of ancient dust may carry the memory of neutron-rich matter flung from a collision before the solar system existed. The light from such an event is called a kilonova. It is not the same as a supernova. A supernova marks the death of a massive star. A kilonova can mark the merger of neutron stars. Powered in large part by the radioactive decay of newly made heavy nuclei in the expanding debris, the glow can begin blue, then become redder as the ejecta expands, cools, and becomes rich with heavy elements that absorb and reprocess the light. The color change matters. It is not only beauty, it is chemistry written across the sky. The early blue light may come from faster, less opaque material. The later red and infrared glow can point to heavy elements whose complex atomic structures make the ejecta more opaque. The fading light becomes a record of nucleosynthesis, the making of new atomic nuclei, happening in matter cast away from the collision. For most of human history, this kind of event was not seen for what it was. Theoretical models suggested that neutron-star mergers could create heavy elements and produce short gamma-ray bursts, but the full chain of evidence was incomplete. Gravitational waves changed that. When detectors measured waves from a neutron star merger in 2017, and telescopes then found light from the same region of sky, astronomy entered a new kind of observation. The event was not seen in one messenger only. It was heard in spacetime and seen in light. The gravitational waves arrived first as a rising signal, a long chirp from two compact objects spiraling together. A short gamma-ray burst followed within seconds. Then, telescopes around the world turned toward the galaxy that held the source. They found a new point of light near a distant galaxy, fading over days and weeks in a way that matched kilonova models. For the first time, the same cosmic collision had been observed through gravitational waves and electromagnetic radiation. This is called multi-messenger astronomy. The name is technical, but the idea is simple. The universe can send news in more than one form. Light carries one kind of information. Gravitational waves carry another. Neutrinos can carry another. Cosmic rays can carry another, though tracing them is harder. When more than one messenger arrives from the same event, the picture becomes less flat. Different parts of the event become visible. A neutron star merger is suited to this because it touches many kinds of physics at once. The gravitational waves reveal the motion of the masses and the way the stars deform. Gamma rays may reveal a narrow jet launched near the merger. Optical and infrared light reveal the expanding ejecta and the elements forming within it. X-rays and radio emission can reveal the afterglow as the outflow strikes surrounding gas. Each wavelength opens a different door. In the days after the merger, the fading kilonova light showed that neutron star collisions can produce heavy elements through rapid neutron capture. It did not mean every heavy element in the galaxy came only from mergers. The full history of element formation remains more complex. Other rare stellar explosions may also contribute, but the observation proved that neutron star mergers are real sites where some of the universe's heavy elements are made. This is a gentler way to think about catastrophe. The collision is severe, but it also enriches space. Matter that once formed the cores of dead stars becomes free again. It expands, cools, decays, and joins the interstellar medium. Over time, it may be mixed into clouds that form new stars. Around those stars, planets may gather. A part of a neutron star merger can become buried inside an ordinary world, silent and solid. The gravitational waves continue outward, long after the light fades. They spread in all directions, weakening with distance, crossing galaxies, passing through matter almost without being stopped. Earth lies in their path only briefly. Detectors wait for the stretching and squeezing. The change is tiny, but the pattern is readable. A chirp rises. Models compare it with possible sources. The masses are estimated. The final orbit is reconstructed. In that signal, the stars are not seen as glowing spheres. They are measured as moving gravity. The final moments carry the strongest information. As the frequency rises, the wave pattern tells how quickly the pair is spiraling inward. If the neutron stars are deformed by tides, the phase of the signal shifts subtly. That subtle shift helps constrain the equation of state. The same question from the interior returns in a new form. How does dense matter push back when gravity pulls? The merger asks the question violently, but the answer appears as a delicate change in timing. After the merger, the central object may live briefly or collapse quickly. If it remains as a hypermassive neutron star for a short time, its rapid rotation and thermal pressure can support it temporarily. Magnetic fields may be amplified. A disk may feed material inward. Jets may form along the rotation axis. If the mass is too high, the remnant becomes a black hole, leaving a disk and ejecta behind. The boundary between survival and collapse is one of the most important unknowns in this field. The same collision can therefore tell two stories. One is the story of matter thrown outward, forming heavy elements and glowing as a kilonova. The other is the story of matter left behind, testing whether a neutron star can still resist gravity or must pass into a black hole. The event is both scattering and concentration, release and collapse. The surrounding space answers slowly. Ejecta expands into the material around the system. A jet, if pointed near Earth, may produce a bright gamma-ray burst. If seen off-axis, the afterglow may rise later as the jet slows and spreads. Radio telescopes may follow the fading remnant for months or years. The merger itself is brief, but the aftermath is not. It leaves a changing cloud of matter, radiation, and motion. There is a sleep-like patience in that aftermath. The first signal passes, the bright light fades, infrared warmth lingers, radio emission grows, then declines. The galaxy returns to appearing quiet, as if nothing happened. Yet the event has changed the inventory of matter there. Heavy nuclei have been made. A compact remnant or black hole remains. Gravitational waves have crossed the universe and moved on. 2 neutron stars may have taken billions of years to reach that meeting. Their massive parent stars lived and died long before. Each core collapsed, each remnant cooled. The pair orbited. The orbit shrank. Then, in less time than it takes a night to pass on Earth, they merged and changed a small part of the universe around them. This is the long rhythm of cosmic transformation. Stars live quickly or slowly. Some die and leave neutron stars. Some neutron stars pair with others. Their orbit tightens through gravitational waves. Their final collision makes light, matter, and a new signal in spacetime. The chain is not dramatic when seen across the full stretch of time. It is patient. It is matter changing homes. The neutron star alone bends time. The neutron star in a pair sends time outward as a wave. A pulse from a pulsar marks rotation. A flare from a magnetar marks magnetic stress. A merger marks the motion of gravity itself. Each form is a different way for the same kind of compact remnant to become visible. The star may be small, but its endings and encounters are not small. They reach across detectors, telescopes, galaxies, and the periodic table. In the dark, after the kilonova fades, the newly made elements drift outward. They do not know names. Gold is not gold there in any human sense. Platinum is not precious. Uranium is not dangerous by intention. They are nuclei, heavy and unstable, or heavy and lasting, born from neutron capture in expanding debris. Only later, in colder places, inside planets and hands and machines, do they acquire human meanings. The collision has no awareness of what it has made. It follows gravity, nuclear physics, radiation, and time. Yet from that blind process can come the material of future worlds. Far away, another pair of neutron stars may still be orbiting. Their path may be wide for now. Their gravitational waves may be too faint to measure. Their merger may lie far beyond the present age of human instruments. Still, the orbit is changing by a little. Energy is leaving. The stars are drawing inward. In some distant dark, 2 collapsed suns are already moving toward a shared ending. A neutron star stands close to the edge of becoming something else, but it has not crossed that edge. This is the careful distinction at the center of the story. Its gravity is strong enough to bend light, slow clocks, crush matter into forms no laboratory can hold, and make a surface where ordinary ideas of weight fail. Yet it is still not a black hole. Light can still leave it. Signals can still escape. A surface still exists. That surface matters. A black hole is defined not by being dense in a general sense, but by the presence of an event horizon. The event horizon is a boundary in spacetime from inside which no light can return to the outside universe. It is not a solid shell. It is not a wall floating in space. It is a limit in the geometry itself. Beyond it, all possible future paths point inward. Escape is no longer a matter of having enough power. Escape has stopped being a possible direction. A neutron star has not made that boundary. It may sit close to the conditions that would create one, but the surface remains outside the point of no return. Light leaving the surface has to climb through a deep gravitational field. It is stretched. Its energy is reduced. Its path is bent. Time near the surface runs slower compared with faraway space. But the light does leave. The star is extreme, but it is still visible. This is why the idea that time fully stops on a neutron star needs to be handled gently. Time does not freeze there in the absolute way the phrase can suggest. A clock near the surface would run more slowly when compared with a distant clock, but local processes would still occur. Matter could move. Radiation could be emitted. The star could rotate. A hot spot could cross the surface. A pulse could travel outward and arrive at a telescope. The slowing is real. The stopping is not. For time to appear frozen to a distant observer in the strongest sense, the object would need to approach an event horizon. A neutron star remains outside that horizon because some pressure inside it still resists total collapse. Gravity is enormous, but not yet final. The compact remnant is held up by the behavior of dense matter, by quantum rules, by pressure arising in particles that have been forced as close together as nature allows under those conditions. This support has limits. No known material pressure can resist gravity without end. If a neutron star becomes too massive, the balance fails. The object can no longer remain a neutron star. Its radius shrinks inside the boundary from which light cannot escape, and a black hole forms. The surface disappears from view, not because it is hidden by smoke or darkness, but because the geometry of spacetime no longer permits a signal to return. The maximum mass of a neutron star is one of the most important unfinished measurements in astrophysics. It is sometimes connected with the Tolman-Oppenheimer-Volkoff limit, the theoretical upper mass for a cold, non-rotating neutron star, supported by dense matter pressure. The exact value is not known because it depends on the still uncertain equation of state. Dense matter decides how hard it can push back. Observations decide which possibilities remain alive. Neutron stars, measured with masses around 2 times the mass of the Sun, already tell an important story. They show that the matter inside cannot be too soft. It must resist compression strongly enough to carry that weight without giving way. At the same time, radius measurements and gravitational wave observations suggest that the matter cannot be treated as infinitely stiff. It must be compressible, but not too compressible. It must hold, but only up to a boundary. The star lives in that narrow allowance. Rotation can help for a while. A rapidly spinning neutron star can support a little more mass than the same star could support without rotation, because the motion contributes to the balance. Heat can also help temporarily after a merger, when the remnant is still hot and turbulent. Magnetic fields may complicate the structure, but these kinds of support can fade or redistribute. A remnant that survives briefly may collapse later, after it cools or loses angular momentum. This is one possible fate after 2 neutron stars merge. The combined mass may be too high for a stable neutron star, but not immediately collapse if rotation and heat provide temporary support. For a short time, the remnant may be hypermassive, held up by rapid differential rotation and thermal pressure. Then, as energy is lost and the internal motion changes, gravity may win. The object slips past the last stable form of matter and becomes a black hole. A delayed collapse leaves a different imprint than an immediate one. It can affect the light from the merger, the disk of matter around the central object, the formation of jets, and the material ejected into space. The boundary between neutron star and black hole is therefore not only a theoretical line, it shapes the signals astronomers receive from the most compact mergers in the universe. In isolation, a neutron star may approach the edge more slowly. If it has a companion, it can draw matter from that companion over time. Gas spirals inward, forming an accretion disk, heating in X-rays, then falling onto the surface. Each layer of accreted material adds a little mass. If the star begins below the maximum mass, it can remain stable. If the growth continues long enough, the margin narrows. The final change may be quiet from far away. There may be no great visible explosion when the surface vanishes behind a forming horizon. The star's structure would fail inward. The last light from the surface would be stretched and delayed. To a distant observer, signals from the collapsing surface would become redder, fainter, and more delayed as the horizon forms. In the local frame of the falling matter, the collapse would continue. Perspective shapes the description. That is one of the reasons black holes and neutron stars sit so naturally together in the study of relativity. Both are compact. Both curve spacetime strongly. Both can form from the deaths of massive stars. Both can live in binary systems, accrete matter, and send signals across space. But one has a surface, and the other does not. One lets light escape after climbing. The other creates a boundary where return is no longer part of the future. The presence of a surface changes everything. A neutron star surface can heat, burst, crack, and send radiation outward. Matter falling onto it can release energy at impact. Hotspots can rotate into and out of view. X-ray bursts can ignite in accumulated layers. Pulses can reveal the star's spin. Light bending can reveal more than half the surface at once. These are surface stories, and they cannot happen in the same way on a black hole. A black hole can have an accretion disk and jets. It can make bright light from matter outside the horizon. But the horizon itself gives no surface flash. Nothing strikes it in a way that sends a signal back from the boundary. The light belongs to the surrounding matter before it crosses the point of no return. The distinction is subtle in images, but deep in physics. A neutron star is therefore a visible edge. It shows what matter can do before the event horizon arrives. Its very existence means dense matter has found a temporary answer to gravity. Not a final answer, not an unlimited answer, but an answer strong enough to keep a surface above the horizon. The question of that answer leads back to the interior. If the core contains only neutrons, protons, electrons, and related particles, the maximum mass will depend on how those particles interact under pressure. If hyperons appear, they may soften the equation of state and make collapse easier, unless other forces stiffen the matter again. If quark matter forms, it may change the radius and stability in ways still debated. The boundary before black holes is written in particles too small to see. Large-scale gravity depends on microscopic behavior. This is the quiet meeting of relativity and quantum physics. Relativity describes the curved space-time around the star, the slowing of clocks, the bending of light, and the possibility of horizons. Quantum and nuclear physics describe the pressure inside the matter, the superfluid, the crust, the possible phases of the core, and the resistance against collapse. A neutron star holds both kinds of physics in one object. Neither can be ignored. Black holes are often treated as the place where known physics reaches its sharpest mystery. That is true in one sense. But neutron stars are just as valuable because they still give information back. They are not sealed completely. They allow observation of matter, under gravity, close to the limit. They are compact enough to test relativity, but not so compact that all surface information disappears. They are difficult, but not silent. Their difficulty is generous. Each mass measurement, each radius estimate, each pulsar glitch, each X-ray burst, each gravitational wave event removes a little uncertainty. The picture does not become simple, but it becomes narrower. The universe offers many neutron stars with different masses, spins, ages, magnetic fields, and companions. Together, they form a scattered set of natural experiments. None is complete alone. Together, they ask where matter ends and black holes begin. There may be objects even closer to the edge than the neutron stars already known. A very massive neutron star with a small radius would be an especially compact remnant, with strong light bending and strong time dilation near the surface. If it rotates rapidly, the shape and stability become more complex. If it has accreted matter, its history matters. If it was born in a merger, its future may be brief. Classification becomes a matter of careful measurement. Sometimes the line between neutron star and black hole is not easy to infer from mass alone. A compact object in a binary may have a mass that falls in a region where the nature is uncertain. It may be a heavy neutron star, if dense matter can support it. It may be a light black hole, if collapse has already occurred. Observations of gravitational waves have made this boundary more than a theoretical question. They have shown compact objects whose identities require caution. Caution is part of the beauty here. The universe does not always label its remnants plainly. A neutron star close to the edge is not waiting with intention. It is not resisting in a conscious way. Its matter follows the available rules. Gravity presses inward, pressure responds. Rotation may help. Magnetic fields may shift energy. If the balance holds, the surface remains. If it fails, the surface is lost. No drama is required. The transition is written in mass, radius, pressure, and spacetime. From far away, the difference may appear as a change in signals. A pulsar may stop if its beam disappears behind a newly formed horizon. An accreting neutron star may lose the surface bursts that once revealed impact. A merger remnant may leave an afterglow shaped by whether a black hole formed quickly or only after a delay. The evidence is indirect, but indirect evidence is how these objects are known at all. The edge before black holes is not a place marked by a visible line in space. It is a condition. It is the point at which dense matter can no longer keep every path from tilting inward. It is where a star that once had a surface becomes an object defined by the absence of return. A neutron star lives just outside that condition, close enough to show its shape, far enough to keep speaking. This makes it one of the universe's most useful remnants. It is a body made of matter, but matter at the last stronghold before collapse. It is a clock that runs slow near the surface. It is a lens that bends its own light. It is a laboratory for nuclear physics, a test of relativity, a source of pulses, flares, bursts, waves, and heavy elements. It is the final visible form of a dead massive star before darkness becomes an event horizon. The journey from the living star to the neutron star has been a journey inward. Fusion gave way to collapse. Collapse gave way to density. Density curved spacetime. Rotation made pulses. Magnetism made flares. The interior kept its secret. Mergers sent waves through the universe and scattered heavy elements into the dark. Now the path reaches the boundary, where the same gravity that made the neutron star asks whether matter can continue to answer. For a neutron star, the answer is temporary. Sometimes it lasts for millions of years, sometimes longer, sometimes only moments after a merger. But as long as the answer remains, the surface remains, and with it, the possibility of light escaping, clocks ticking, pulses arriving, and information crossing the distance. A neutron star is not the end of reality. It is the last visible pause before one of reality's deepest thresholds. Small, dense, and quiet in the dark, it holds its place against gravity for as long as matter can hold. Around it, time bends but does not vanish. Light struggles but still leaves. The surface remains. For now, that is enough. Even after the boundary before black holes has been reached, the neutron star does not stop being useful to the universe that studies it. It remains a kind of fixed weight in the dark, a place where several great ideas meet without fully merging into one another. Matter, gravity, magnetism, light, and time all gather there, not as separate subjects, but as parts of one compact object that still allows signals to escape. This is what makes the neutron star different from a final darkness. It is close to the edge, but it is not sealed away. It can still be measured. Its surface can still send X-rays. Its magnetic field can still shape particles. Its rotation can still mark time. Its orbit, if it has a companion, can still reveal gravity through tiny changes repeated over years. The star may be small and far away, but it gives back pieces of itself in every signal that leaves. The pieces are never whole. No observation carries the full interior. No pulse opens the core. No gravitational wave translates dense matter into a simple answer. Each signal is partial, shaped by distance, geometry, temperature, field strength, and motion. But partial does not mean weak. A pulse arriving a little early or a little late can reveal an orbit. A small change in X-ray brightness can narrow the size of a star. A fading glow after a merger can show that heavy elements were made in the expanding debris. This is the slow work of astronomy. It does not touch the object. It waits for the object to speak in light, timing, and gravity. A neutron star is also a reminder that the universe does not separate violence from patience. The birth is sudden. The collapse happens in moments. The supernova throws the star's outer layers into space. But the remnant can remain for immense spans, cooling slowly, spinning down slowly, changing its magnetic field slowly. The event that forms it is brief. The object that remains can become part of cosmic timekeeping for millions of years. A pulsar turns a death into a rhythm. A magnetar turns stored magnetic energy into rare flashes. A merging pair turns a long orbit into a final wave passing through spacetime. These are not different stories in isolation. They are different expressions of the same kind of remnant. The neutron star is dense enough to hold many futures inside one name. Some neutron stars may fade beyond easy detection. Their beams may never point toward Earth. Their surfaces may cool until their light is faint. Their magnetic fields may weaken. They may become almost invisible, wandering through the galaxy as dark, compact objects, still massive, still curved around by gravity, but nearly silent. They would not stop existing simply because they are no longer easy to see. The galaxy may contain many such quiet remnants. Some were born before Earth formed. Some may have crossed through spiral arms, through old clusters, through regions of gas that later formed other stars. They carry no memory in the human sense, yet their motion is a record of ancient supernovae. Each one is the endpoint of a massive star that once burned brightly and then lost the balance that held it open. Others remain active enough to be found. A radio beam crosses Earth. An X-ray hotspot rotates into view. A binary companion feeds material onto the surface. A burst appears after years of quiet. Each detection is a small opening in the dark. The object is not nearby, not reachable, not visible as a landscape, but it becomes present through measurement. A point in a catalog becomes a physical place. The physical place is difficult to imagine because it is smaller than the scale associated with stars and heavier than the scale associated with worlds. It does not belong neatly to either category. It has a surface, but not a habitable one. It has gravity, but not planetary gravity. It has a crust, but not rock. It has an atmosphere only in a compressed and unusual sense, if it has one at all. Every familiar word becomes a borrowed tool. The borrowed words still help. Surface, crust, core, field, pulse. They let the mind move near the object, without pretending that the object is familiar. A neutron star asks for both humility and precision. It can be described, but not fully domesticated by comparison. It can be measured, but not held inside one simple image. The most useful image may be that of pressure. Pressure from gravity, pressure from dense matter, pressure from magnetic stress, pressure from the past of a massive star folded inward. Nothing about the object is spacious. Even its emptiness has been taken away. The atom, so roomy in ordinary matter, has lost its scale. The particles are crowded. The star is a compressed answer to the question of how far matter can be pushed and still remain matter. Beyond that answer lies the black hole. Before that answer lies the ordinary star. The neutron star stands between them, not halfway in size or brightness, but in meaning. It is the last form in which the collapsed core remains visible as matter with a surface. It is the last compact body that can show the struggle between gravity and pressure directly. In that struggle, time becomes part of the evidence. Clocks near the star slow, relative to clocks far away. Pulses arrive with steady intervals, then slowly lengthen as rotation loses energy. Binary orbits shrink through the emission of gravitational waves. Cooling takes place across long spans. Magnetic fields decay and rearrange. Time is not only a subject near neutron stars, it is one of the tools by which they are known. A pulsar is measured by time. A merger is detected through a changing wave pattern over time. A cooling remnant reveals age through temperature and light. A glitch, exposes an abrupt exchange of rotation inside the star. The neutron star does not simply bend time near its surface. It leaves timing marks across every way it is observed. There is a quiet unity in that. The object born from collapse becomes a clock, a lens, a laboratory, and sometimes a forge. It keeps the history of a star, tests the behavior of matter, shapes the path of light, and sends signals that can cross the galaxy. It is not large, but its influence passes through several scales at once. At the smallest scale, the behavior of particles decides whether the core can resist gravity. At the scale of the star, mass and radius decide how strongly spacetime curves. At the scale of the binary, orbits lose energy through gravitational waves. At the scale of the galaxy, pulses move through interstellar plasma and map what lies between stars. At the scale of cosmic history, mergers scatter heavy elements that may later become part of planets. The neutron star gathers all of this without intention. It does not choose to mark time or make elements or test theories. It simply follows the laws that shape it. The meaning comes from the fact that those laws meet there in a form that can still be read. Not everything can be read yet. The core remains uncertain. The maximum mass remains uncertain. The exact origin of magnetar fields remains uncertain. The full pathway from neutron star mergers to all heavy elements remains under study. The emission mechanism of pulsars still contains open details. These unknowns do not weaken the subject. They keep it alive. A finished object would be less useful. A neutron star remains partly open because its signals continue and its interpretation is not complete. The best way to leave it is not with a final answer, but with the image of continuation. Somewhere, a pulsar is still sending radio pulses across a thin mist of interstellar gas. Somewhere, a magnetar's crust is holding magnetic strain beneath a surface bent by gravity. Somewhere, an old neutron star is cooling so slowly that its change would disappear inside a human lifetime. Somewhere, two compact remnants are orbiting each other, losing a little energy with every turn, their final meeting already written into the curve of their path. All of these objects began with massive stars. They began with light, heat, fusion, and balance. They became collapse, density, pressure, and curvature. They remain as small bodies with long consequences. The supernova light fades quickly compared with what follows. The remnant endures. That endurance is the last calm before the true ending of the journey. The neutron star can be left in its place now. Not solved, not reduced, not made ordinary. It can remain a compact weight in the night, still turning, still cooling, still bending the rhythm around it, while the wider universe moves on in its slower dark. The neutron star remains far behind now, a small dark weight in a sea of distant light. Its surface still holds against gravity. Its hidden core still keeps the pressure of matter pressed to the edge of understanding. Around it, space is curved, and time is slowed. But from far away, it becomes only a quiet point again, folded into the larger night. The supernova that made it has thinned into a faint cloud. The pulses, if they come, cross the galaxy in patient intervals. The magnetic field turns with the star, unseen except where light and particles answer it. Somewhere else, two remnants may still be orbiting, drawing closer by the smallest loss of energy. Not hurried, not delayed, only following the shape of spacetime. Beyond them, the galaxy continues. Gas drifts through spiral arms. Old stars cool. New stars gather inside clouds too dark to see clearly. Light travels for years, then centuries, then longer, arriving quietly wherever something is waiting to receive it. The universe does not need to finish its sentences quickly. It leaves them stretched across distance, carried by gravity, radiation, and time. The journey can soften here. No new object has to appear. No final answer has to be forced open. A neutron star can remain what it is. The last compact memory of a massive sun, small enough to hide in darkness, heavy enough to bend the rhythm around it, and patient enough to keep turning long after the fire that made it has faded. The surrounding dark grows wider. The pulses become farther apart in thought. The curved light fades. The dense star is still there, but the mind can let it drift back into the quiet field of night, where all things move slowly, and even time seems willing to rest. Is greater than, is greater than, is greater than. End of script. Sleep well.